Hi everyone, welcome to PLA Academy. I hope you found this video helpful. If so, I'd really appreciate it if you could subscribe to my channel, like this video, share it with your friends, and leave a positive comment. Your support and encouragement motivate me to create more great videos. I divide the topics in Unit 1, Mechanics and Materials, as follows, like this. And all the topics are covered by following the syllabus of the Physics International A-Level for Edexcel, as shown here. In this video, I've covered all of Topic 2, Materials, focusing on the fluids. Density is defined as mass per unit volume. We calculate the density by ρ equals m over v, where ρ is density in kilograms per cubic meter, m is mass in kilograms, and v is volume in cubic meter. Density is specific value for each material, meaning that same material will always have the same density. The density of an object can explain whether it will float or sink in a liquid. If the object's density is more than the liquid's density, which caused the object to sink. If the object's density is less than the liquid's density, which caused the object to float. For example, a block of aluminum will sink and settle to the bottom of a liquid. This shows that its density is more than the liquid. A block of ice will float at the surface of liquid, but will be totally submerged. This shows that its density is equal to the liquid. A block of cork will float at the surface of a liquid, with some of it submerged. This shows that its density is less than the liquid. Pressure is defined as the force per unit area. We can write the equation of the pressure as P equals F divided by A, where P is the pressure in Newton per meter squared, or Pascal, F is the force in Newton, and A is the area in meter squared. We can conclude that the pressure increases as the contact area decreases while the force remains the same. In the opposite way, the pressure increases as the force increases, while the contact area remains the same. Pressure in a liquid. Pressure in a liquid act on an object in all directions. The pressure is higher at the greater depths in the liquid, resulting in a higher force acting on an object compared to shallower depths. Pressure decreases as the object rises through the liquid. The equation of pressure in a liquid is P equals ρ g h, where P is pressure in newtons per meter squared, or pascals, ρ is the density in kilograms per cubic meter, g is the acceleration of free fall, which is 9.81 meters per second squared, and h is the depth in meters. We can prove this formula. If the container is filled with a liquid, the pressure in the liquid at the bottom of the tank is the force divided by the base area. The force is the weight of a liquid, which is equal to the mass of the liquid multiplied by gravity. The mass of the liquid is density of liquid multiplied by the volume of the container. The volume of the container is equal, the depth multiplied by the base area, so the pressure at the bottom is equal to F over A. By substituting the force F with W equals mg, substituting the mass m with ρ, V, and substituting the volume V with HA, we can derive the equation P equals ρ gh. Upthrust is the upward force that a liquid or gas exerts on a body floating in it. Upthrust force, also known as buoyant force, is caused by the difference in hydrostatic pressure at the bottom and the top of an object immersed in a fluid. We can write the equation of the upthrust U equals ρ gv, where F is the upthrust in newtons, ρ is the liquid density in kilograms per cubic meter, g equals gravity in meter per square second, and v equals immersed volume of the object in cubic meter. We can prove the formula of the upthrust as follows. Pressure at the bottom, P2, is greater than pressure at the top, P1, resulting in a greater upward force, F2, than downward force, F1. This difference in forces, F2 minus F1, is the upthrust F. P1 equals ρ gh1. F1 equals P1 times A, where F1 is the force due to P1, so F1 equals ρ gh1A. P2 equals ρ gh2. F2 equals P2 times A, where F2 is the force due to P2, so F2 equals rho g H2A. Therefore, the upthrust F equals F2 minus F1, factoring rho g A, like this, substituting H2 minus H1 equals H, like this, and substituting AH equals volume V, like this, so F equals rho g V. Therefore, we can conclude the Archimedes' principle that an upthrust force equal to the weight of fluid displaced by the object. Work example. An object in the shape of a cube of side 200 mm is placed in a liquid of density 1.8 times 10 power 3 kilograms per cubic meter. Its top surface is horizontal and is 350 mm below the surface, as shown in figure below. A. Calculate the pressure from the liquid at the top surface. We calculate the pressure P due to liquid by P equals rho g H. Substituting rho equals 1.8 times 10 power 3, g equals 9.81 and H equals 350 times power negative 3. We solve the pressure P equals 6,200 pascals for two significant figures. B. Calculate the pressure from the liquid at the bottom surface. We calculate the pressure P due to liquid by P equals rho g H. Substituting rho equals 1.8 times 10 power 3, g equals 9.1 and H equals 550 times power negative 3. We solve the pressure P equals 9,700 pascals for two significant figures. C. Calculate the downward force caused by the liquid on the top surface. We calculate the force at the top by F equals P times A. Substituting P equals 6,180.3 and area A equals 200 times power negative 3 multiplied by 200 times power negative 3. We solve the force F equals 250 newtons for two significant figures. D. Calculate the upward force caused by the liquid on the bottom surface. We calculate the force at the bottom by F equals P times A. Substituting P equals 9,711.9 and area A equals 200 times power negative 3 multiplied by 200 times power negative 3. We solve the force F equals 390 newtons for two significant figures. E. Calculate the net upthrust on the cube. The net upthrust equals force at the bottom minus force at the top, like this. We solve the upthrust F equals 140 newtons for two significant figures. G. What condition needs to be satisfied for the cube to float up to the surface? The upthrust is greater than the weight of the cube, causing the resultant force to act upward. This caused the cube to float. F. Archimedes' principle states that the upthrust on a body in a fluid is equal to the weight of fluid displaced. Show that this is true for your calculation in A. 2E. The weight of the fluid displaced equals mg, substituting m equals rho v. Substituting rho equals 1.8 times 10 power 3, v equals cubic of 200 times 10 power negative 3, and g equals 9.81. We solve the weight equals 140 newtons for two significant figures. This shows that the weight of liquid equals the upthrust. Viscous drag acts on objects moving through fluids. The fluids are represented the liquid and air. When an object moves through a fluid, or a fluid moves past an object, you get friction between the surface of the object and the fluid. This is viscous drag. Therefore, viscous drag is the frictional force between the surface of an object and a fluid, acting to oppose the object's motion through the fluid. You can calculate the force due to viscous drag on a spherical object moving through a fluid using Stokes' law. The equation of Stokes' law can be written as F equals 6 pi eta R V, where F is the viscous drag in newtons, eta is the viscosity of the fluid in newtons, second per meter, R is the radius of the object in meters, and V is the speed of the object is moving in meters per second. Viscous drag depends on the viscosity of a fluid. As the viscosity increases, the drag increases. And the temperature in liquids increases, the viscous drag decreases, while gases get more viscous as temperature increases. The Stokes' law only applies to small objects moving slowly with laminar flow. Laminar flow is a flow pattern where all the parts of the fluid are flowing in the same direction and the layers in the fluid do not mix. Laminar flow usually occurs when a fluid is flowing slowly or when an object is moving slowly through a fluid. In the diagram shows a ball falling slowly with laminar flow, and this is the laminar layers. Turbulent flow is a different flow pattern. You don't get nice layers like you do with laminar flow. All the parts of the fluid get mixed up. Turbulent flow usually occurs when a fluid is flowing quickly or an object is moving quickly through a fluid. In the diagram shows a ball moving quickly with turbulent flow. Stokes' law only applies to small, spherical objects moving slowly with laminar flow. It doesn't apply to turbulent flow. Terminal velocity in the liquids. Viscous or drag force of liquid is the resistance force when an object travels through a liquid. It depends on the shape, speed, and temperature of liquid. A metal sphere dropped from rest will reach terminal velocity as it falls through the liquid, like as shown. At the start, the resultant force acts on the metal is weight minus upthrust, causing it accelerate downward, and its velocity increases. The drag force increases upward as velocity increases, so the resultant force is weight minus upthrust minus drag force, causing the resultant force to decrease and acting downward, leading to the acceleration also decreases, and the velocity increases at slower rate. The drag force increases until the resultant force is zero, meaning that weight is equal to upthrust plus drag force, causing the acceleration is also zero, and the velocity remains constant. This is called terminal velocity. Recall that the upthrust and weight are always constant, while drag force increases from zero to maximum when a ball reaches terminal velocity. To determine the viscosity of a liquid, you can calculate the viscosity of a liquid by timing the fall of different sizes of ball bearings, little steel balls, of known density, ρ, using an experiment like this. Record the density, ρ, of ball bearing in the table below. Fill a wide clear tube with the liquid you want to investigate, for example, washing up liquid. Make sure you know the density of the liquid, sigma. Put one rubber band about halfway down the tube at a position such that the ball bearings will have achieved terminal velocity when they reach it. Place two more elastic bands below the first so that the distance between each band is equal and the lowest band is near the bottom of the tube. Measure and record the distance, d, between each band. Measure the diameter of your ball bearing and halve it to get the radius r. And then record the radius r in the table below. Drop the ball bearing into the tube. Start a stopwatch when the ball reaches the first band and record the time at which it reaches second band as T1 of the third band as T2. Record your results as T1 and T2 minus T1 in a table, see below. Calculate the terminal velocity at time T1 and T2 minus T1 using the distance d divided by each time taken and then record in the table. If the velocities at T2 minus T1 are consistently larger than those at T1, the ball bearing might not have reached terminal velocity when you started timing, so move the electric bands down the tube a bit and try again. Repeat this at least 3 times for each ball bearing to reduce the effect of random errors on your results. Calculate the average terminal velocity of the ball bearing between the elastic bands. Then repeat the whole thing for different sizes of ball bearing. If the ball falls close to the wall, redo the reading. This causes the flow will no longer be laminar and Stokes' law will not apply. You can then calculate the viscosity, eta, of the liquid. The ball bearings are falling at terminal velocity, so the sum of the forces acting on the ball is zero as weight of the ball bearing minus upthrust minus viscous drag is equal to 0. Substituting the equation weight is mg, upthrust is sigma gv, and viscous drag is 6 pi eta rv, where m is the mass of sphere, which is ρ 4/3 of pi cubic r. where V is the volume of a ball bearing, which is 4/3 of pi cubic r. We rearrange the equation to give the viscosity of liquid as this, where r is the radius of the ball bearing, g is the gravitational field strength due to gravity, ρ is the density of the ball bearing, sigma is the density of the liquid, and v is the average terminal velocity between the elastic bands. Exam-style question. A student carried out an experiment to determine the viscosity of washing up liquid using the apparatus shown. A. The student released the sphere at the top of the cylinder and made measurements, using a stopwatch and meter rule, so the terminal velocity of the sphere could be determined. 1. Describe a method that the student could use to determine an accurate value for the terminal velocity of the sphere. You may add to the diagram above. Put one rubber band about halfway down the tube at a position such that the ball bearings will have achieved terminal velocity when they reach it. Place two more elastic bands below the first so that the distance between each band is equal as d, and the lowest band is near the bottom of the tube. Measure the distance, d, between each band. Drop the ball bearing into the tube. Start a stopwatch when the ball reaches the first band and record the time at which it reaches second band as t1 of the third band as t2. Calculate the terminal velocity at time t1 as distance, d, divided by t1, and terminal velocity at t2 minus t1 as distance, d divided by t2 minus t1. If the velocities at t2 minus t1 are consistently larger than those at t1, the ball bearing might not have reached terminal velocity when you started timing, so move the electric bands down the tube a bit and try again. Repeat this at least 3 times to reduce the effect of random errors on your results. Calculate the average terminal velocity of the ball bearing between the elastic bands. You will get 5 marks from. Place 2 or more rubber bands pore markers on the cylinder. The top band should be far enough below the surface for terminal velocity to have been reached. Measure time for the sphere to fall a given distance and measure distance fallen. Reference to repeated measurements and averaging. Calculate the terminal velocity by dividing the distance between markers with time between markers. 2. Explain why the use of larger sphere would increase the percentage uncertainty in the calculated value of the terminal velocity. A larger sphere has a larger weight, which results in a greater terminal velocity. Consequently, the larger sphere takes more time to reach its terminal velocity. However, as the terminal velocity increases, the time it takes to fall a certain distance decreases. This leads to an increase in percentage uncertainty because while the absolute uncertainty in the time measurement, due to the stopwatch and reaction time, remains constant, the measured time interval for the fall becomes smaller. You get 4 marks from. A large sphere would have a greater terminal velocity. Weight is greater due to a large sphere, so takes more time to reach terminal velocity. The time of falling would be less due to the greater terminal velocity. The absolute uncertainty in the time is the same. B. 1. Complete the free body force diagram for the sphere when travelling at terminal velocity. There are 3 forces to act on the sphere as follows. The upthrust acts upward. The viscous drag acts upward. The weight acts downward. You get 3 marks from correct upthrust force, correct viscous drag, correct weight. 2. The student obtained a value of 0.16 meters per second for the terminal velocity of the sphere. Calculate the viscosity E of the washing up liquid in Pascal second. Radius of sphere equals 4.8 times 10 power negative 3 meters. Weight of sphere equals 3.5 times 10 power negative 2 newtons. Density of washing up liquid equals 1.1 times 10 power 3 kilograms per cubic meter. The resultant force acts on the sphere is 0 when the sphere reaches terminal velocity. So, the weight of sphere minus upthrust minus viscous drag is equal to 0. Substituting the upthrust is liquid's density times gravity times volume of the sphere, and the viscous drag is 6 pi eta r v. Substituting the volume of the sphere is 4/3 pi cubic r. We rearrange the equation of the viscosity like this, substituting the weight, liquid's density, gravity g, radius r, and terminal velocity v in the equation like this. We solve the viscosity of the liquid as 2.1 pascal second for two significant figures. You will get 4 marks from the equation of weight of sphere minus upthrust minus viscous drag is equal to 0. Use the equation of upthrust as rho g v. Use the equation of viscosity as 6 pi eta r v. Correct the viscosity as 2.1 pascals second.
I hope you found this video helpful. If you did, I would be grateful if you would subscribe, share, like and leave a positive comment. Your support will encourage me to create more content. Thank you.